Hey everyone, and welcome to this Masterclass Explainer. Let's talk about a scenario that really separates the amateurs from the absolute pros. Anyone can match a standard existing shade by just tweaking a known recipe, right? But picture this. A customer drops a brand new, completely unknown sample right on your desk and says, build a formulation for this, or develop a totally new shade from scratch. Wow. For a lot of folks, that is exactly where the real struggle begins. But today, we're going to eliminate that struggle. We're going to master exactly how a professional R&D engineer develops a zero-base formulation right from the ground up.
So here's our roadmap for today. We'll kick things off with the formulation mindset, then move into reading the shade, selecting primary pigments, building base formulas, balancing cost and performance, and finally, we'll wrap up with trial records and quality.
All right, let's jump right into section 1, the formulation mindset. Okay, let's dive into this. Before we even touch a beaker or a scale or, a single gram of pigment, we need a complete paradigm shift in how we approach our work. Think about it. Color matching is essentially just copying a standard shade. It's a totally reactive process. Formulation development, on the other hand, is what we're really aiming for here. This is true color design. As a formulator, you're making proactive, calculated choices. You're deciding exactly which pigments to use, the total number of pigments, the necessary strengths, the precise opacity, and the ultimate cost. You aren't just copying. You're literally engineering a solution. Moving right along to section 2, reading the shade. Now, this is the first practical, hands-on step of the whole process. You absolutely must decode the physical sample in front of you before you even think about building the formula. It's kind of like a giant puzzle. So ask yourself, how do you actually read a shade? When a customer hands you a piece of plastic with a super complex color, how do you visually break it down into data you can actually use? What are the specific visual checkpoints? Well, you've got to run it through these 5 critical visual checks. First up, what is the main hue? Second, is the sample light or dark? Third, is it bright or is it a bit dull and muted? Fourth, is the material transparent or is it completely opaque? And finally, does it lean warm or is it cool? Seriously, I want you to memorize this list. Answering these 5 questions correctly gives you your entire formulation direction. It takes all the guesswork out and replaces it with a solid, structured roadmap. Let's ground this theory with a really concrete example. Imagine a customer brings you a light green sample. A professional visual analysis is going to yield these specific results. Okay, it's light, it obviously has a green hue, but if you look a bit closer, it has a slate yellow undertone and it is fully opaque. Just like that, you instantly know you're going to need white for the opacity and lightness, green for the main hue, and just a touch of yellow to hit that specific undertone. Which brings us to section 3, selecting primary pigments. Now that we have our detailed visual analysis, we need to choose our core ingredients. And we do this based on what's often called the golden rule of pigment selection. It's a very strict sequential order. Step 1, select your main color, your primary pigment. Only after you establish that solid base do you move to step 2, which is selecting your correction colors. One of the absolute most common amateur mistakes is just throwing 4 or 5 different pigments into the mix right at the very beginning. That is a totally chaotic approach. You really need a calculated, sequential build.
And your strategy for choosing those primary pigments? It depends entirely on the end application. If you need a highly bright shade, you're going to lean heavily towards organic pigments. For an outdoor shade that has to survive intense sun and weather, you absolutely need the UV resistance of inorganic pigments. Premium automotive shades almost always require a highly specific blend of organic and inorganic to get both brightness and durability. And for a pure, blinding white shade, well, you rely on high-quality titanium dioxide, or TiO2. If your primary hue is blue, you reach for phthalo blue. For red, maybe quinacridone red. For green, phthalo green. The application literally dictates the chemistry.
All right, section 4, building base formulas. This marks the turning point where we stop visually analyzing and start mathematically calculating our recipe. Now, what's really interesting about this exact breakdown is the math for the pastel green formula we analyzed earlier. To achieve that opaque, light look, we formulate a really heavy base, 60% TiO2. Then we add just 5% of our primary green pigment to establish the hue, and the remaining 35% is our polymer carrier, the actual plastic-based material. Breaking it down this way makes the math incredibly clear and digestible. You mix the specific ratio, you take a molding trial in the lab, you check the result against the customer's sample, and then you apply your correction colors based on the difference. And as you're mixing these ratios, please let this relieve some of your stress. Formulation is never perfect in one trial. 3 to 10 trials are absolutely normal. Actually, scratch that. It's not just normal, it's expected. So many beginners get completely discouraged when their first trial isn't a perfect match. Don't be. Professional R&D is a highly iterative process. Taking molding trials, checking the results, and methodically correcting them, that is exactly what mastery looks like. Next up, Section 5, balancing cost and performance. Because look, formulation isn't just art, it is a commercial business. Customers want a great color, for sure, but they also demand consistency, chemical stability, and super strict cost control. Let's compare Formula A and Formula B. Both of these formulas achieve the exact same standard of performance. The visual shade is absolutely identical, but Formula A costs 450 rupees per kilogram to produce, while Formula B costs only 320 rupees per kilogram. The crucial takeaway here, if the performance is completely equal, the lower cost formula is undeniably the professional choice. That's cost optimization in action. But wait, saving money means absolutely nothing if your formulation fails this next crucial test. Is the formulation heat stable? Just think about an engineering plastic like ABS, which is often processed at a scorching 240 degrees Celsius. If your carefully crafted color yellows, fades, or just burns out at those high temperatures because you used a cheaper, unstable pigment, the entire formula has to be completely rejected. You always have to test for the real-world processing environment. Finally, we arrive at Section 6, Trial Records and Quality. Now, it might seem like basic housekeeping, but maintaining meticulous documentation is the absolute backbone of professional formulation development. A good evaluation log brilliantly illustrates what a pro's workflow looks like. You log the formula number and the exact pigment percentages. But more importantly, you log the hard scientific data. Things like the LabStar color space values, which give you precise numerical data on lightness and color channels, and the delta E, which calculates the exact visual difference between your trial and the customer's target. Finally, you leave detailed remarks, and you track this for every single trial. I promise you, this habit alone transforms you from a guesser into a true engineer. Before we wrap up, let's quickly review the classic traps. You want to avoid these common amateur mistakes at all costs. Using way too many pigments right out of the gate instead of finding your primary base. Ignoring cost targets until the formula is completely finished. Completely neglecting those high-temperature heat stability checks we just talked about. Failing to maintain your trial records so you literally forget how you arrived at a color. And the ultimate sin, conducting direct production trials on the factory floor without doing rigorous, small-scale lab testing first. So you now have this structured mindset and the exact process to build a shade from absolutely zero. But I want to leave you with a question. Are you ready to master the single most demanded topic in the entire plastics industry? I'm talking about white Masterbatch formulation. In our next explainer, we are going to dive deep into advanced TiO2 selection, the incredible impact of optical brighteners, and exactly how to troubleshoot those really tricky white shades. It is a fascinating subject, so take everything you learned today, apply it, and get ready for the next level.
So that's how a new color set is developed from scratch, starting with the resin selection, pigment choice, formulation, trials, color measurement, and final production approval. Remember, successful color formulation is not about randomly mixing pigment. It's about understanding color science, pigment interaction, processing behavior, and customer requirement. A small change in pigment loading, processing temperature, or polymer grade can completely change the final set. That's why color development requires both technical knowledge and practical experience. If you found this video valuable, don't forget to like, share, and subscribe to Sipet Polymer Tech. We regularly share practical knowledge on color matching, masterbatch formation, polymer processing, troubleshooting, and quality control that you won't easily find anywhere else. And here's a question for you. Have you ever faced situation where the lab set matched perfectly but the production set came out different? Share your experience in the comment below. We may discuss your case in an upcoming video. Thank you for watching. Keep learning, keep innovating, and I will see you in the next video with another practical plastic industry topic. Thank you.